talk, so you can follow the math more closely.
Okay, yeah, so finally, yeah, let's do a board talk. Like if you don't mind, you can actually sit closer because it might be difficult to see from far but away. But anyway, so the talk is actually based on, I'm going to talk about random graph matching, but this time I'm going to focus on the so-called low degree polynomials and then talk about the limits of local algorithms. The talk is actually based on like the 3 papers. So the first 2 actually is co-authored with Chen, Yihong, and then Sophie. So these are the 2 papers. And then when I talk about the limits of local algorithms, I'm going to talk about the recent work by Ganasani, Masulier, Semergen. So they actually look at a very interesting problem called correlation detection. Okay, so let's get started. Okay. Yeah, sorry, 2023. Yeah. I'm still thinking that I'm living in 2023, but it's 2023. Okay, yes. Let me try again. Yeah, it's not that dark enough, I guess. Maybe this one? Sorry. Yeah, this is better. Okay, good. So let's actually first recall the hypothesis testing problem that we talked about. Yeah. Hello? Okay.
We mounted. What about now?
Does that sound better? Huh? Okay, sure. Yeah, so I'm going to talk about that first we call the. Okay, let's see. I think it's good here. Yeah, so let's say test, how it works. Still noise? Let me actually reset. Do that again. Test. Hello? Sound good?
There's just nothing we can do about it. I mean, we're in a different room.
Should I continue? Should I continue? How it works?
Yeah. It's noisy, I don't know.
Okay.
It's not that noisy. I think it's reasonable. It's at a similar level, I would say.
Okay.
Yeah, let's just continue.
Yeah. Anyway. Okay. Then I'll continue. Okay. Okay, so let's start by recalling the hypothesis testing problem that I introduced in the previous lecture. So basically, under the null hypothesis, we have 2 order Xuanyi random graph. Let's say the adjacency matrix are A and B. So there are 2 independent order Xuanyi with n nodes, and then edge probability is Q. Okay. And under H1, then there are actually 2 row correlated order Xuanyi with n nodes edge probability Q. So the marginal distribution are the same, but under alternative, the 2 graphs are correlated. So in particular, I meant that there exists an underlying permutation pi such that if I look at the edge connections Aij and B pi I pi j, so like the correct, the pairs of these edges under the correct correspondence, they are RAD disputed as pairs of Bernoulli random variable with probability Q and correlation rho. Okay, so that's what I meant when I say there are 2 row correlated order Xuanyi random graphs. That means there's some underlying mapping or permutation. Then under this correct mapping, if I look at the pair of edges Aij, B pi, pi j, there are RAD disputed as a pairs of Bernoulli Q with correlation rho. Okay, so in particular, if I standardize the adjacency matrix entry Aij, I subtract its mean and divide it by the standard deviation. I do the same thing for my second graph, Bij. So I standardize that. Then basically, I mean, if I look at the correlation between A bar ij and B bar pi I pi j, so this should give me like this correlation coefficient rho, right? So that's just the precise way that I meant. Okay. It's just a side note. So in the previous lecture, I talked about this subsampling model, if you still remember. There I introduced this like slightly different parameter, like NPS. So P is the edge probability for the parent graph, S is the subsampling probability. If you want to map them, the rho is roughly S minus 1 minus P, like 1 minus PS. Okay. Okay, but I'm actually going to focus on this more general way of defining the correlated graphs. Okay. Okay, so that's the problem. If you have this problem, hypothesis testing problem, so like the estimation problem, like every time we start with the max likelihood estimation, here we can also start with the so-called like the optimal test is actually given by this likelihood ratio test. Okay, so basically, if I call the distribution, the joint distribution of A and B under H0 is like a Q, let me call it a Q, and the joint distribution of A and B under H1 is P, so then I can look at the likelihood ratio, right? So let's say I define the likelihood ratio as L, so it's just the ratio of P divided by the probability under Q, right? Okay, you can further expand it out by actually using, the total probability formula. You can first conditional on the underlying permutation pi under the H1, then you can write in this form. Okay, right? So basically, I just single out the underlying permutation pi. This is the conditional distribution of A and B given pi. And the QAB, other than now, there's no pi, so it's still QAB. Okay. So one thing is that, even though this is an optimal test, but computationally, if you want to evaluate this, you want to compute this expectation, which also means that you need to, this involves n factorial permutation, right? Does it make sense, right? So that's why if you want to directly evaluate this expectation, at least it's computation intractable, because you need to do this n factorial times. Okay, so that's why we need to come up, if we want to get efficient algorithms, then we need to actually see how can we derive an efficient test. Okay. Okay, right. So it turns out that there's a very general, common approach to derive computation efficient test. So this is actually these low degree polynomials I'm going to talk about. So to obtain a computationally efficient test, okay, so we're actually going to use these low degree polynomials. In particular, these ideas actually come from, I think the first paper to actually use this idea is this Hopkins and Sterner back in 2017. And then the Hopkins further developed this in his PhD thesis. And then after that, there's a very nice survey coming out by Kuniski, Wayne, and Bandera at 19. So they basically this is a very nice survey. They basically describe in general how this low degree polynomial approach works. Okay, so high-level idea is that they're going to project this likelihood ratio I mean, you can think about it's a function of the entries aij, bij. So you want to project this onto some space of low degree polynomial. Okay, and the hope is that to compute these low degree polynomials, you can do it more efficiently instead of directly computing this like a range. Okay, sounds good. Yeah, and then feel free to interrupt me if you have any questions or you want me to clarify a little bit. So now to define this projection, then we need to define like what's the proper space, the inner product, right? So in particular, we're going to define inner product between two functions. Let's say I take f and g. So f and g is like any functions that maps, in my case, is adjacent matrix 0, 1. And then I have two adjacent matrices, A and B, right? So that's why I want to map 2 times and choose 2 pairs of this like a 0, 1 entries into some real number. Then I can define their inner product. It's just the compute the product of them under the non-distribution Q. Okay. Right, makes sense? Okay, now after I define this, now I can think about the space of functions, okay, under this inner product, so that I can talk about the orthonormal basis. So now let's introduce an orthonormal basis, in particular the orthonormal polynomial basis. Okay, so how it is defined? In fact, there is a very, it's actually very simple. So I'm going to use this phi indexed by S. S is basically 2 sets. So S is like, you can write as S1, S2. And then S1, S2 is just a subset of pairs. For any S1, S2, that is a subset of all the entries 2 pairs. Okay, and then what is this basis looks like? It's very simple. It's just given by this standardized Aij. So it's A bar Ij, Ij in S1, and times B bar Ij, Ij in S2. Okay. Okay, so let's take a closer look, right? So this is a polynomial indexed by S. S is just consists of both S1 and S2. S1, S2 just a bunch of like pairs or edges, like choosing from like entries 2 pairs. And then I just take the A bar Ij, multiply, the product of all Ij in S1 and do the same thing for B bar Ij. Okay, we can quickly.
What does bar denote here?
Oh, bar just means that subtract the mean divided by standard deviation, the one that I just introduced earlier. It's a standardized that. So it has 0 mean and the variance is 1. Yeah. Okay, so we can quickly check a few things. For example, if I look at this basis, if I evaluate its mean under Q, so this should be 0 as long as this S is not empty. Okay, right? Because under Q, A and B are independent. When you take expectation, it's already centered, so that's why the mean will evaluate to be 0, right? Since I mentioned it's also normal basis, so we can quickly check the inner product between phi S and phi T. So I take 2 different S and T. This should be evaluated to indicator where S is equal to T. Okay, so again, let's quickly check this. Why is the case? Okay, so basically I take the expectation of phi S and then times another phi T, right? Again, I'm taking expectation under Q, so A and B are independent. So I really should look at this A bar Ij, and then you have another one says T1 and then A bar Ij, right? So now the crucial thing is that S1 and T1 has to coincide. Otherwise, you will have some edge only appear once, and you take expectation, this will become 0. Does it make sense? Right? So for this expectation to not vanish, S1 has to equal to S2. Sorry, T1, S1 has to equal to T1, S2 has to equal to T2. So that's why you will have this indicator, like S equals T. Right? Okay, so that also verifies why I call it also normal basis. Another thing is that you can check the phi S is that S polynomial, where S, I mean, is coordinated of S1 plus coordinated of S2. So it's a degree coordinated of S polynomial of the entries, of the entries of A and B. Right? Because what I'm doing here is just I take the bunch of multiplication of A and J, like Aij stuff, and then you just need to see how many are there. They're coordinated by S1 plus coordinated by S2. So that's the maximum degree, right? So that's why it's a polynomial. Any questions? Also good? Yeah. So now once I have this polynomial, then I can talk about what's the so-called optimal projection, like the optimal degree, like polynomials of certain degree. So there's a notion called optimal. Let's say I restrict the degree to be 2k, like at most 2 capital K polynomials. Okay, so how to do that? When I say optimal, I mean I want to find out the polynomial that maximizes the following quantity. So I look at the mean of this polynomial under my distribution P. So the distribution under alternative hypothesis divided by, say, the standard deviation under distribution Q. Okay, so I want to maximize over all the polynomials where the degree of this polynomial is upper bounded by 2k. Okay. So why this is like a natural quantity to maximize? Well, if you think about, you want to do the hypothesis testing, right? So the F is just like some combinations of phi S. The phi S has a mean 0 on the Q, right? So now if you want to separate these two different distributions using this F, you want to make sure first the mean of F is large. In fact, you want to make sure the mean of F is large compared to the variance, or like standard deviation. So in particular, here I look at the standard deviation on the distribution Q. Okay, so you can think about this is like a signal to noise ratio for this problem. If you can make this larger, that means this F is more powerful to distinguish this hypothesis. I mean, not exactly quite, because here we only look at the variance under Q. If you want to prove this works, you also consider variance under P. But anyway, this is just a natural notion to start with, like to maximize. Okay. Okay, so let's see actually what's the optimal degree 2k polynomial. So one thing that you could do is that you can actually use the likelihood ratio and write this as inner product. It's the inner product between likelihood ratio and L and an F. Okay, why is the case? It's because I'm just using the change of distribution. I change this underlying distribution to Q, so then I pay a factor of likelihood ratio L, right? This guy, if I want to write it, can be written as like F and F, right? I mean the second moment, right? Okay, so then you can see that basically this is already in the form of where you can apply Cauchy-Schwarz, right? This is like maximizing the inner product of F with respect to the likelihood ratio, but then you want to divide it, normalize by the inner product of F with itself, right? So then by Cauchy-Schwarz, okay, so the first thing is that the inner product between L and F, I can write this as using this notation. So like, because F is a degree 2k polynomials, right? So it lives in the space where it's spanned by these 2k polynomials. So I can basically look at this notation means that I project L onto the space of polynomials with degree at most 2k. So these should be equal, right? Make sense? And now I can further apply a Cauchy-Schwarz inequality. So then this should be less or equal than the inner product of this projected likelihood ratio, and then times the inner product of f with respect to self, right? So this is the Cauchy-Schwarz step. And then when you achieve this equality, so when you achieve this equality, so the maximum is achieved when you pick this f to basically to be the same as this projection of the likelihood ratio, right? So then you achieve this inequality. And then you see that this divided by this, so that's exactly the quantity I want to maximize. So then basically, this is the one that maximizes this ratio. Right? One thing I actually comment that is that so far what I talk about is actually very generic. You can do that for almost any hypothesis testing problem, right? So it's not really restricted to this graph matching problem. But there's indeed one restriction is that when you have this orthonormal polynomial basis, you want to make sure the distribution Q is relatively simple, like a product distribution. So that's why this is an orthonormal basis. If you have a more complicated distribution Q, then it's not that clear to find out what is the the orthonormal basis anymore. Okay, so you do need some condition on the distribution Q. Yes?
Could you please repeat why we take the mean with respect to P and the variance with respect to Q?
Oh, it's just like some proxy of this separation. So let me draw a picture. I mean, it's not fully accurate, but roughly says what's going on. So let's say this is a 0. So this is actually the mean of f under Q. Okay, because f is a bunch of combination of phi s. The phi s has mean 0 under Q. And now you want, if you say the mean of f is here. Okay, so if you look at the distribution, I mean, okay, so there may not be a Gaussian, right? But you will have some distribution centered at 0 or centered at mean of f. So this is the case where you correspond to h0. This corresponds to h1, right? And then you have this like a fluctuation, right? So the fluctuation here is roughly controlled by square root of like the standard deviation or this, right? So now you want to make sure this mean separation here is much larger than this standard deviation. So then you can indeed actually separate out this distribution by picking a threshold like in the middle. Okay, so that's why we want to maximize this ratio. Does it make sense? At least? Yes?
What is the space of functions here?
Yeah, the space of function, I guess, is all the functions that map this 0, 1 to real number endowed with this inner product.
But then this polynomial that entire because I have only like 2 times n choose 2 polynomials, but that's
okay, that I agree.
No, it does. I think.
It does? Okay, if you include all the degrees? Yeah, you can include all the degrees.
So this
Yeah.
space of function is actually finite dimension.
oh, this is finite dimension? Wait, so this is the basis, this is just 2 times n choose 2. That is
Yes,
the dimension?
Yeah, exactly. Yeah, I think so. Now it's, yeah.
So you don't get any square cube.
Well, it's not 2 times n choose 2, right? It's n choose 2 square.
Oh, sorry, n choose 2 square.
Yeah.
Oh.
And is it because this is only 0?
Yeah, it's only 0, 1. You can just basically list all the table and look at the entries to some extent, right? Yeah.
And when you say a degree to 2k subspace, so now are you saying that now if I restrict to only degree 2k polynomials, that subset is indeed a subspace in this of this space?
I think so.
That's
Then
not
I think
obvious,
so.
right?
You mean that's?
If you give me a 2k
I think that's
vector basis, it's obvious, but that's not what this is.
I think it's already in the form of vector space. If you have the inner product, you have the basis. So you only look. So basically, the 2k means all the I mean the space spanned by this basis.
S1 plus S2 less than or equal to 2k.
Yeah,
Okay,
yeah,
okay, I see,
exactly. So I think it's a subspace. Yeah. Okay, good. But yeah, thanks for the clarification. Okay.
It is S1 plus S2. I was confused about that too. It's not S1 times S2.
I mean, if we're looking at all possible S1, S2, then
Yeah, so I think,
the size of the basis will be.
yeah, so the degree is correlated with S1 plus 2, but the how many such as is, yeah. Okay, so it's getting weak. So the F star, as I said over there, the optimal estimator is given by the projection of this like ratio onto the space of the degree of at most 2k, right? So I can write it according to the basis, right? So that's what I'm going to write, where I constrain the correlated of S to be at most 2k, right? Okay, so there's actually some very simple fact you can check under this optimal projection is that if you want to evaluate the mean of this optimal polynomial under P, so what you want to do is that you can think about this as an inner product between the likelihood ratio L and F star. If you plug in here, you will immediately get that's 2k and then L phi S squared, right? You can also try to evaluate now the second moment of F star under distribution Q. This is just the inner product of F star with respect to itself, right? Okay, so now this is also normal basis, right? So, I mean, phi S is also normal basis. So the inner product between F star with respect to itself is just basically given by this coefficient square, right? K L phi S square, right? I mean, you can also plug in here. You will see that you have sum of S, sum of T, but then S has to be equal to T for this to be non-vanishing. So you will get the coefficient square, right? So basically what I'm saying is that now if you look at the optimal, maybe I'll use a different color. So if you look at the optimal SNR, remember this is given by this ratio. And this is just given by square root of summation of S. Sorry, the S where S is less than 2k, and then L phi S square, right? Make sense, right? So that's basically some calculation that I have. Now let's actually specialize this to our problem. Okay, so then we need to compute this coefficient, right? So if I want to figure out what's exactly the SNR, I need to compute this quantity. Okay, so now I just need to plug in, right? So this is the same as the expected value of P under phi S. And then remember, what's my definition of phi S? That's just a bunch of product, right? Like ij in S1, aij, and then ij in S2, but I standardize that. Make sense? Okay, and one thing is that P actually is the distribution under alternative, right? There's underlying permutation pi, so let me actually split into two. At first, condition on pi, and then look at the expectation of P condition on pi. Okay. Let me also, I think that's good. Okay, so now if I look at this quantity, okay, so now let's take a closer look, right? So I look at the expectation of P condition on pi, and look at a bunch of this aij bkl, right? So for this to be non-vanishing, you have to like match every A bar ij to some like B bar ij under the permutation pi. Does it make sense? Right? Otherwise, if you have a single A bar ij that is not matched, if you take expectation, it will give you 0. Right? So that means that this is equal to 0 if this means that I map every ij in S1 to like some pi I pi j. So then this map has to be equal to S2, right? Okay. Otherwise, I mean, if this is not equal, so then it will be 0. Otherwise, then you can basically computing like if you do that is like A bar ij, B bar pi pi j, right? And then that expectation is exactly rho, the coefficient, the correlation coefficient. So then you have rho to the power of correlated to 1, right? Make sense? Okay. And now, if you do a further step, so this is the inner like expectation. You also have to take expectation over pi, right? But that's simple, right? Because this will give you the indicator, right? So that means that this should be equal to, again, 2 cases. So let me actually put it up a little bit. So you will have, in one case, is that like S1, this means like isomorphic to some particular unlabeled graph H. So then this should be rho H and times the probability of pi S1 equal to S2. Okay. Otherwise, if S1 and S2 are not isomorphic, then you get a 0, right? Because if S1, S2, they are not isomorphic, there's no way you can pick a permutation pi such that pi S1 equal to S2, right? Okay. So now, if you want to complete this, you just need to figure out what's the probability of pi S1 equal to S2, given that S1, S2 are isomorphic, right? Okay, so this one, it turns out that it's just 1 over this quantity called a sub. Let me write it down first. This is sub n h. This means that these are copies of h in this complete graph Kn. Okay, so h is just, you can think about it as a template. It's unlabeled graph. You just look at the topology. You do not look at the known labels. You figure out, you look at complete graph, how many copies there are. And this probability should be equal to 1 over that. Why? Because pi S1 is mapped to one of these copies. And then you have so many number of copies, so the probability you kind of hit this S2, like a particular copy, is just given by 1 over the number of copies. Make sense? Okay, good. So then that means this quantity here, okay, let me write it down here. It just means times this, and then 1 over this sub n h, right? So I'm actually going to call this like AH in my notation. This only depends on h. Okay, if I fix this rho and then n. Okay, so basically now I evaluate this guy, so I can plug in, I can get the optimal estimator. Sorry, like the optimal SNR. Okay. Okay, so let me actually now plug in this. Let me first evaluate what's exactly the F star. So remember, this is the expression of F star. I already compute this coefficient. Now I can plug in. So basically that means I have to sum up over H, where the correlated of H is at most K, and I have a coefficient AH. I have a sum over S1 has to be isomorphic to H, and then I have this bunch of IJ in S1 A bar IJ, right? And then I have a sum over S2 isomorphic to H, and then IJ in S2 B bar IJ. Right? So you can see that here S1, S2 has to be like they are both isomorphic to a particular edge. So I kind of change my summation over S, divided into sum over unlabeled graph edge, and then S1, S2 both are isomorphic to edge. Okay. And now if you style this is actually relates to the so-called signed subgraph count. So if I can denote a notation, let's say WH a bar. Okay, why it's related to the subgraph count? It's because if you pretend there's no like a bar here, like not centered, then here is just basically computing how many copies of H graph A, right? But you center that and you standardize that, so that's why people call it signed subgraph count, because A now could be like either minus Q or 1 minus Q. Okay, but it's just a generalization of the subgraph count. And here is just the subgraph count, the signed subgraph count under the graph B. Okay, so basically this optimal like optimal polynomial. So what it's doing is just to try to take the signed subgraph count of particular edge in graph A times the signed subgraph count of this particular edge in graph B, take the multiplication weighted by this parameter edge, and then sum over all the possible edge. Okay. If you think about why this is kind of useful to detect the hypothesis, it's because under the non-hypothesis, these A and B are independent, so the signed subgraph count should be uncorrelated. But under alternate hypothesis, A and B are correlated. So if you see large value of this, you expect to see large value of this. So that's why they are correlated. So that's why you're possibly able to determine or distinguish this hypothesis using F star. So that's actually how the subgraph count appears in this calculation. Okay, and also if you look at the optimal SNR, like this ratio, if you plug in here, so if you plug in this expression now, it's just square, right? So it's again, you can break the summation into H, where the H is correlative H is at most K, and then you square that, so you have AH square, and then you have two summation S1 sum, like sum of S1 isomorphic to H, sum of S2 isomorphic to H, and then you put 1 here, right? Okay, so this guy, if you think about that, so if you sum over basically all the the copies of H, right? So this summation should give you exactly the sub n H parameter, square that, because you do the double summation for S1 and S2. Okay, so then what you get is AH squared times the sub n H squared. So if you remember, my definition of AH is here. If you square that and then times the sub of n H squared, so these will cancel out. So you get a rho to the power of 2H. Right, so this whole thing just becomes the sum of H, where the correlative H is at most K, and then times rho to the power of 2H. Correlativity. Okay? Make sense? Okay, so one thing is that, I mean, if this quantity is bounded, somehow, like this is SNR is bigger than 1, then that means that this optimal low degree polynomial really cannot reliably distinguish these two hypotheses, right? Because actually the picture that I draw there, right, before. So that's why, for example, when people want to understand what's the limits of this like a low degree polynomial, they actually try to study when actually this optimal SNR is bounded. Bounded means even you increase the size of the graph, it still like stays as a constant. Okay, so you can actually get some estimate now, right? For example, let's try to understand like when this quantity will be bounded. Well, then you need to do two things, right? The first thing is that this guy here should decrease when you have a larger like H, right? But here the summation may actually, you have more terms, right? You have more graphs. right? So now if you want to bound that quantity, you need to actually have an estimate about how many like unlabeled graphs of edge with the given edges. Okay, so there's a very coarse estimate. So if you look at unlabeled graph edge, let's say with k edges, then we know it actually has at most 2k vertices. Because here I'm looking at the induced graph, right? If you give me like a bunch of edges, right? So at most you have 2k like vertices, right? And then based on this, you can get an estimate about the number of such graphs. Then it's at most you have 2k choose 2 possible pairs to choose from, and you want to choose k of them, right? Does it make sense? Right? Because you have 2k vertices, they have at most 2k choose 2 pairs, can possibly connect them, and you want to connect k of them. So that's the upper bound, right? Okay, if you do a little bit algebra, this is a rough upper bounded by 4ek to the power of k. Okay. Make sense? Okay.
What are you counting here?
Oh, I'm just trying to illuminate all the possible edge where you have this edge have k edges. Sorry? There's no like n anymore in this. Here I'm just looking at the edge. It's unlabeled graph with at most k edges. Yeah. So this expression, the n actually already disappears. Yeah. 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 There's no. Yeah, so I'm just kind of looking at all these different possible unlabeled graph, like the different topology that you can form with k edges. It's a loose upper bound, but it turns out that this already gives us something.
So can you explain this again? How did you get this 2k choose 2 and k?
Oh, because you have at most 2k vertices.
Right.
And now you have 2k vertices, then how many node pairs? There are at most 2k choose 2 node pairs. Mm-hmm. Right. And then how to form a graph is like connecting those node pairs. So that's why I have 2k choose 2 and then choose k. Does it make sense? Right. So so you don't think about, so you first have edges, so then you have these 2k vertices, don't connect them. Right? And then you have so many pairs, you're going to connect them in some way. You want to choose k of them. So that's how it, at least how it goes, roughly. Okay, so now I can try to bound this quantity in this optimal SNR. So I can weight it according to the number of edges in this edge. So let's say the number of edges is going from 1 to capital K. And how many such graph? I bounded by 4e little k to the power of k, and then times rho to the power of 2k, right? Make sense? And you can see that this will be bounded if like you can say basically like a rho squared times k is order 1. So it means, for example, let me just loosely write in the form that if k is like poly log n and rho squared is 1 over poly log n. Okay, so why, sorry, this polylog and this polylog n, I mean, the exponent may be different. So let's say this is a log n to the 3, this probably you should pick log n to the 4th or something. Okay, but you may wonder why I pick this particular polylog n. Why I cannot have a larger k. This is because of this low degree hardness conjecture. So it basically says that if you look at it's basically saying that if you look at these polynomials of degree at most polylog n, And if they fail, then they conjecture that all the polynomial algorithm will fail. So it's a very strong conjecture. Okay. So if you believe this conjecture, then in this case, what it means is that if rho square is smaller than polylog n, then actually this problem is hard for both testing and the estimation, like the graph matching problem, are computationally hard. Okay. So once again, so basically the conjecture says that I look at all the polynomials of degree at most polylog n. If they fail, they conjecture that all the polynomial algorithms fail. Okay. So then if you believe that conjecture, then this means that if rho square is 1 over polylog n, then for this graph matching problem, for both testing and estimation, they are computationally hard. This is actually consistent. We are not able to break this barrier. But this is actually much bigger than IT limit. IT limit, in certain cases, you can rho can be 1 over poly n instead of polylog n. Okay, so there's a big gap between the IT limit we introduced earlier versus this computation limit, like the conjecture. Okay. Make sense? Okay. Yeah. So this is a negative result for these low degree polynomials. We actually be able to prove a positive result. So we're not able to get, but we're getting relatively close. So basically, we're able to show that for both testing and the recovery, like the graph matching problem, actually computationally easy. When actually this rho square is bigger than a particular constant alpha, it's roughly 0.338. So this is actually what people call Altair's constant. And this appears when you try to count how many unlabeled trees of size k, like with k edges. So this actually turns out to grow as 1 over alpha to the power of k. Okay, so this constant basically determines how fast this number of unlabeled trees with k edges grow. And then we're able to show that as long as the correlation rho square is bigger than this constant, then we're able to use this low degree polynomial to achieve both testing and recovery. Okay. Okay, yeah, I think that's the next thing I want to talk about. But maybe we can have a break, and then I can continue from there. Okay. Yeah, that's much. Hello? Hello? Is that good? Yes. Okay, let's continue. Okay, so I'm going to talk about efficient testing based on these low degree polynomials. You see that this optimal estimator, this optimal polynomials is actually just given by the subgraph count. Right? But it turns out that if I want to get efficient testing, we should actually restrict subgraph, like subgraph count to tree count. Okay, so let me actually first write down what I mean by tree count, and then I will tell you why we actually restrict this to tree count. Okay. So if you restrict to the tree count, let me just use this like FTAB to denote this optimal, this low degree polynomial based on tree count. So basically, it's just now you look at all the unlabeled trees of a given size, let's say k edges. Okay, And then the form is the same as before. It's actually coming from this optimal low-degree polynomial projection. It's given by this AH and times the subgraph count of H in A times the subgraph count of H in B. Right? In fact, there's a way to view this as an inner product between two vectors. Okay? Where I define this vector WA bar is just given by the square root of AH and then WHA bar for all H in this unlabeled tree. Okay? You can view this as a so-called graph feature. Okay? You can. So basically, what I'm doing is that I look at all the possible unlabeled trees with k edges. Every coordinate corresponds to one particular tree. Look at the subgraph count in A, and then times the square root of AH because I have this weighted coefficient here. Now I have this very long vector, right? You can view this as some like feature vector for this graph. It captures the characteristics of the graph, and now my test statistic, what we're doing is just take the inner product of these two feature vectors, one for A, one for B. Okay, and then the hope is that if A and B under the null hypothesis, they're independent, so they should be roughly uncorrelated. In the alternate hypothesis, A and B are correlated, so that's why these two feature vectors are also correlated. Yeah, do you have a question?
Sorry, is T the set of all trees?
Yeah, the T. Yeah, let me write down here. T is a set of all unlabeled trees with k edges, let's say. So I'm going to focus on this. T is the set of unlabeled trees with k edges.
What is K?
K is the parameter that we're going to choose. Yeah, yeah. Okay, so then the precise theorem that we prove is the following. So suppose this NQ is not that small. It's n to the minus little 1. And then rho square is bigger than alpha. And here I'm going to choose my K is growing, but it's not growing too fast. Like it's order of log n over log n. Then we can show that if you look at this test statistic, the probability is less than a threshold tau under P plus the probability of this statistic bigger than tau under Q is little of 1, where tau is 1/2. It's kind of the mean of this statistic under P. Okay. So basically, this is the formal statement, like the formal theorem that we proved. Okay. So here it also tell you what's the range of k that we're going to choose. K is actually growing with n, but it's not growing too fast. And then when rho square is bigger than alpha, then when this NQ is not that too small. So this n to the minus little 1 means that just like it cannot be like. I mean, this is the average degree, right? So it can tolerate when the average degree is a constant, but it cannot like going like to 0 too fast. Okay, it can be like 1 over poly log n, so that's fine. Okay, then this like type 1 or type 2 error actually goes to 0. Okay. Okay, so let me actually give you a little bit of the proof sketch. It's actually, I mean, we actually already did almost all the computation. So the first thing is that if you look at this statistic on the Q, okay, so that's my statistic for the tree count. So if you look at the so you're going to evaluate the sign subgraph count on the A, and then they're already centered, so it's 0. Right? Okay, so that's why the mean is 0. I mean, we actually did that before. The next thing is that the mean under P is actually the same as the of this statistic under Q. So that's the same thing that we evaluated before. And if you remember, this one should be given by now. H is sum over, sorry, you sum over H all in this unlabeled trees H, and then rho times 2H. And remember, I focus on the T is the with k edges. So this is nothing but rho to the power of 2k times the cardinality of this tree, right? And then remember, this guy, as I talk about, this grows as 1 over alpha to the power of k. Okay? So you can see that this will definitely go to infinity if rho squared is bigger than alpha. So that's where this condition come out. Okay, so this actually already showed that this SNR that I defined earlier, if you look at the mean of Ft under the second moment or the standard deviation of Ft under Q, so this already goes to infinity, provided rho squared bigger than alpha. Okay, but now to show this succeed in testing, you still need to further show this ratio, but now you divide it by the variance under P, right? This you still want to show this go to infinity, right? Because you also want to compare the mean separation with the fluctuation under distribution P, right? So this actually turns out to be the key part. So this is the key remaining challenge in this proof. It's just to bound this variance of Ft under P. Okay. Yes.
Sorry, I might be going back a bit, but so when you say that recovery is possible, it's with high probability, I'm assuming, right? Not
Yeah.
recovery. Okay.
I mean, here's the testing. Yeah.
Just I guess general question, because you said earlier that recovery is also possible with.
Oh yeah, recovery means with high probability. Yeah.
Is exact recovery possible for like a different value of Q, say, assuming that Q is large enough that there aren't any isolated vertices?
Yeah. So you need that.
Oh, okay.
Yeah. So for exact recovery, in addition to rho squared bigger than alpha, you need this additional condition, saying that the graph is connected. So that's the more or less the only condition you need. Yeah, but that's a good point. I actually didn't really write down rigorously what I meant by that. Yeah. Okay. I think this is the part we actually crucially utilize the tree property. Okay, to actually control the variance. Unfortunately, actually, I won't go into the detail because this is more complicated. But at least this is the place where I use the tree property. Okay. I mean, as you can roughly imagine, like to bound that variance, you need to consider some copies of graph and look at their overlap. And then if you restrict to the trees, it's more or less easier to deal with. Yeah. And also there's a simple property of trees just saying that the number of vertices is the number of edges plus 1, so it's not that dense. So that also helps. Okay, but anyway, I guess, yeah, that will take me too much time if I want to go in that detail. But there's another thing that I want to talk about. Another motivation, like why we restrict to trees, is from this computational perspective, right? Because at the end of the day, all these calculations that we were doing is try to get some efficient algorithms, like in this case for testing, right? So I need to tell you how I can efficiently compute this polynomial, like this FTAB, right? Does it make sense? And then remember here, I needed this k to be growing. So it's not that straightforward, right? Like how to get the efficient algorithm. So in particular, if I want to evaluate that statistic, then I need to see how I can compute the subgraph count efficiently, right? So let's say I go focus on this generic setting where I have a particular edge. Edge is a tree, and then do the subgraph count if I write it out like this way. So M is either A bar or B bar in my case. Okay. Okay, so the naive way is just to do exhaustive search, right? So what I meant is that I can look at basically all the possible pairs, like IJ pairs, right, of K edges, and then try to evaluate this product and take the sum, right? But then that will take me at least like n to the k time, because I have like n choose k like a possible like edges to check, right? So then my k is actually growing to infinity, right? So this is actually super polynomial. It doesn't do the polynomial time algorithm directly. Okay, so somehow we need a way to efficiently compute that instead of just doing exhaustive search. So it turns out that there's a nice idea in the theoretical computer science. When you try to count the trees, you can do this trick called a color coding. So it's given by Alan Houston and the week 1995. Okay, so let me briefly explain to you the idea. I mean, this is something is needed, like if you want to do this low degree polynomial like stuff, because at the end of the day, the degree will be large, so you need some technique to be able to compute this. Okay, so basically the idea is the following in this case. So you're going to assign some random color. Let's say it's like a mu. To each vertex. So say like random coloring mu to each vertex in the graph from, let's say, a subset like k plus 1. It just means 1, 2, 3 up to integer k plus 1 uniform and random. Okay. So basically, suppose you have the graph here, right? Okay, so why I pick a k plus 1 is because I have a tree with k edges, then it has k plus 1 vertices, right? So basically I'm going to color them. I mean, so I don't have like k plus 1 colors, but you can imagine you have different colors, and then you just color, like just assign a random color for every vertex, right? Okay, so that's the first step. It's just color the vertices just randomly and then uniformly. Okay. And then once you color every vertex, then you can define this so-called colorful graph. All the different. Okay, so what is the colorful subgraph count? Let me using this notation. So again, I'm counting a particular unlabeled tree edge using this after doing this random coloring. So basically, I'm going to have the same summation and the same product here. I mean, this is the same as the initial subgraph count. The only thing that I add is this indicator saying that this S has k plus 1 colors. Okay. So in other words, when I count the trees in the graph, I just want to make sure every vertex will have a distinct color. Okay, so in total you have k plus 1 colors. So that's why it's called a colorful subgraph count. Okay. The reason why they're using this is because this will help them to, I mean, eventually if you want to evaluate this colorful subgraph count, you can use that dynamic programming together with a recursive tree structure. But let's see what's the connection between this subgraph count, this colorful subgraph count, with this original subgraph count. Well, if you evaluate the expectation of this colorful subgraph count with the expectation under the randomness of this coloring, then this is what? Well, just do here, right? You only average over the randomness of this coloring, so that means you just take the probability of this event, right? So well, what you have is that you have S as omega to H, the probability of S has k plus 1 vertex colors, right? And then you have the product S and Mij, right? Okay? And then what's this guy? Well, this is just a simple calculation, right? You have k plus 1 vertices, what's the probability? Each of them has like a distinct color. So that should give you k plus 1 to the power of k plus 1, and then k plus 1 factorial, right? Okay? And then everything else you can combine together, so you get back the subgraph count W, right? So it's just, I mean, the mean is just some scaled version of this. So this roughly, if you do the Stirling like approximation, it's roughly like 1 over e to the k, right? Okay. So now you have this. So this is like some like unbiased estimator of the true thing, right? If you think about this is the quantity you want to estimate, this is the random one because it's random coloring. So then you get some unbiased estimator, right? And then if you want to get a good approximation of this, what you do is just generate a bunch of random colorings and take average, right? So that's how you can get some good approximation of that. So that's exactly what they do in the next step. Is to generate, let me call this quantity like, call it R. R is just some scalar. So you generate roughly 1 over R, independent random colorings. Mu, let's say it's mu t. And then you just take an average. So you can approximate this subgraph count by taking the average from t from 1 to 1 over R, and then this colorful subgraph count on the different random coloring. Okay, you can call these right-hand quantities like a W hat H bar, H like M. Okay, so you may wonder why I choose 1 over R is because the probability here is R. So I want to have enough copies so that I can average out like the fluctuation. Okay, so now the last step is that you need to still evaluate this guy, right? This subgraph, this colorful subgraph count. So if I give you a particular random coloring, how do I compute this one, right? So this turns out to be that you can do very efficiently using dynamic programming. At least when the H is a tree. You can do that like in n squared exponential on the order of k. Okay, so k is the number of edges. So it's n squared exponential to the k. And then k is like a log n over log n in our choice. So that's why it's still polynomial. In fact, we're actually going to choose k to be much smaller than log n over log n. So in the end, in our application, this only contribute n to the power of little 1. So the time that we would get is actually n to the power of 2 plus little 1. Yeah. But let's see actually how you can do this dynamic programming. Here again, I won't go to the details. I mean, this exact algorithm is very complicated. But the rough idea is the following. And then maybe I can also, you can see why the colorful, like this colorful subgraph count will be useful in this. So let me draw a particular tree as an example. Maybe let me draw over there so you can see clearly. Yeah, this is just a toy example to illustrate the idea. So let's say I have a tree like this. Okay, so I'm actually going to look at a particular edge, like this edge here. And then this will break the entire tree into 2 parts. Let's say this is like the T1, and this is like a T2. Okay. Okay, so basically I want to count, like suppose this is the tree that I want to count, right? I want to count like how many colorful like trees like this, right? So it turns out that what I can do is that suppose you already count the colorful trees, like T1, like T1. You also already count the colorful trees of T2. Then you can try to take this and piece them together. The only thing that you want to make sure is the color here should be disjoint from the colors here. So then the vertices won't actually overlap. Does it make sense? Right? So basically, you're going to take the number of counts here times the number of counts here, but then you want to make sure the color are distinct. So that's where the color actually play a role. If you don't have the color, then you will have an issue that you will have some overlap, like overlapping vertices. You will not get a valid tree. So the color helps you to do that. And then you do the weighted count. So you also need to times like this weight here. Let's say this is node I here, this is node j. So you just times mij. So at the end of the day, roughly the dynamic programming is like the count of this tree should be equal to the count of this subtree times the count of this subtree times mij, and then sum over all the possible colors that you can put in this. But then you want to make sure the color are actually disjoint. Yeah. But anyway, this is a good exercise for dynamic programming. I don't want to go too much details here for the sake of time. Okay, sounds good. Okay, so basically now I get this like approximated tree count. Then I can just plug in my test test statistic, and then I can get the approximation. And then in the end, I will still need to show this this approximation error is negligible, but that's not that hard to show. Yeah, because you already have a big separation, so you don't need to be very accurate in this count. Yeah. Question?
So yeah, so basically you're gonna run this algorithm 1 over r times.
Yes.
For each template h.
Yes.
And you have what was it, 1 over alpha to the k as the number of templates of h, right?
Yeah, exactly. 1 over r. Yeah. Yeah. And then r, you remember, also is exponential in k, so you will have exponential in k, these random colorings. But then again, k is much smaller than log n over log n, so it only contributes n to the power later 1 time, at least in theory. Yeah. Yeah, but that's a good point. Yeah. Any questions? Okay. Now let me just briefly talk about recovery. I actually don't want to go into the details. But let me just briefly talk about at least how you can now use this low degree polynomial for recovery. Okay. So the recovery question is that now you want to distinguish, you want to determine whether you're going to match I to J or not, right? So again, I mean the idea is that now you want to get some feature vector for every node, instead of just entire graph. Right? Because now you want to use this feature vector to help you to kind of match them. So how you can define a feature vector for every node? I mean, we talk about how you define the feature vector for the entire graph, just basically counts all the subgraphs, right? But it turns out that this is relatively easy, because you can just use this so-called rooted subgraph count. So you're going to pick a particular root and then just kind of stick that node to that stick the root to that particular node, and then just count how many root the subgraph. So more precisely, you can define this rooted subgraph count. So for particular node I, now I have a tree, let's say h. I want to define a rooted subgraph count. It's basically the sum over. Now I'm going to look at this. I mean, this part is exactly the same. So let me write it down here. So this later part is exactly the same as before. The only thing here is I change it here. So this notation means I'm going to look at the subgraph rooted at I. Okay, and then my template or my unlabeled graph is also a rooted tree. Yeah. Okay. So for example, just give an example. So what does a rooted tree look like? for example, I have like this wedge. So I'm going to count like how many wedges. Like, I mean, if I designate this node to node I, then how many wedges that are incident to this node I. Okay. I can also have a more complicated tree structure like this, and then I can just continue in this way. Right. So that's just how the rooted tree looks like. Okay, and now you can define a feature vector for every node. So let's say for node I in graph A, you can define a feature vector. It's like exactly the same as before. Square root of A edge. Now just change this to be a rooted subgraph count. Okay, and then you can also define node J in B. Let's say it's TJ. It's the same thing, but it's a rooted subgraph count in B. Okay, and now you can define a similarity measure between node I and J just by taking their inner product. Okay, if we expand it out, that's very similar to the test statistic that we've seen before. The only thing now is that you focus on a particular node pair I and J. Okay, makes sense, right? So it's just a very direct generalization, right? From this graph feature now to a node feature. Yeah. I guess I will. So for the sake of let me talk about local algorithms. So maybe I don't want to go further here because it would take too much time. But let me just make a few comments. The first comment is that we still need a rho square bigger than alpha. I mean, that you can possibly imagine because we're still looking at the trees. You can evaluate the mean and the variance, and you want to make the ratio like go to infinity. Like this will pop up very naturally if you do the computation. So the next thing is that it turns out that the very important thing is that we cannot focus on all the trees anymore. So that's where this so-called chandelier come from. So we actually focus on a very particular set of special trees K structure with K edges. Okay, this is actually this notion called chandelier come from. Okay. I'm actually not going even to draw that because that will take some time. But the crucial thing is that even I look at these very special subtrees, the cardinality of this is still like alpha, but I insert a little 1 here and then to the minus. Okay. So to some extent, these special trees are still, they're locked. Because, eventually this power of the statistic will depend on how many trees are there. So even I focus on the special one, there are still many. So that's very crucial for me to get this rho square bigger than alpha. But this special property, this special tree will help us to bound this variance of this phi j. So that's a key thing. So the mean of phi j is pretty easy to compute. The variance of phi j is very complicated. It turns out that if you look at all trees, this is very hard to bound, and it's possible that it's not even bound. It's possible like it is like unbounded. So the key technique there we use is that we focus on some special trees with very special structure help us to bound this variance. But if you're interested, you can look at the paper. It actually gives you a very nice drawing of this chandelier, how it looks like, and more intuition. Yeah. Any questions about this?
Is the recovery exact recovery?
Yes, yeah, there is exact recovery. Yeah, so I didn't say that. So for exact recovery, you need a little bit more, not just rho square bigger than alpha is not enough. You also need this like n, it's basically nps square bigger than, sorry, in this case nq s is bigger than log n, like this connectivity condition. So then, sorry?
What was S?
Yeah, S is the subsampling model. Like in this case, it should be rho plus, let me, yeah, I think I don't remember, yeah, 1 minus rho q, I don't know, something like this, yeah.
Roughly rho.
Sorry?
Roughly rho.
Yeah, roughly rho if q is small, I think, or something, yeah. I mean, this is needed, like even information theoretically, because you will have like isolated nodes or that kind of things. So then basically the idea is that once you have this, and then once you have partial recovery, you can boost it using these correctly identified nodes as a seeds, and then try to slowly match all the rest of the vertices. So there's another step of boosting step to kind of get to the exact recovery. Yeah. So in the remaining 20 minutes, maybe let me talk a little bit about the limits of the local algorithm, and then tell you why this rho square bigger than alpha also appears in other contexts. Okay, so what is exactly the local algorithm? Well, here I'm not going to do very rigorously, but it's like more or less matches our intuition. Like a local algorithm should output a set like S of node pairs such that two things. First, this true pair should be contained. Oh, sorry, I run too much, going too fast. Such that this whether a particular pair is in this set should only depend on some function that applies to a local neighborhood of this I in graph A and the local neighborhood of B. Sorry, no, J in graph B. Okay, so basically the local algorithm will restrict the attention, like this matching decision that you make only depends on their topology of the local neighborhood. Okay, makes sense, right? So it's kind of intuitively that all makes sense. So that's a local algorithm. And now, ideally, for this local algorithm to work, what we want is two things. The first is that for the true pair, right, it should be contained in this set with at least constant probability. So I can get a like constant fraction of the nodes, true pairs in the set. Second, I want all the fake pairs there's only a vanishing fraction of fake pairs in the set. Okay? So the local algorithm will give me a set of node pairs they're decided to match. And these pairs, this S should contain like constant fraction of the true pairs, and it should contain like vanishing fraction of a fake pair, right? I mean, that's one idea. No, this is actually it's like the partial recovery notion, okay? Now the question is that, okay, if you focus on these local algorithms, if you want to get this, then what's the best you can do? If you just restrict your attention to these local algorithms, right? So it turns out that in the sparse regime, so I'm going to focus on the sparse regime, where Q is just lambda over n for some constant lambda. Okay. So in this regime, there's no hope to get an exact recovery, by the way. But I can still possibly get this, right? Okay, why I focus on the sparse regime is because now in the sparse regime, there's a very nice thing is that if I look at the local neighborhood for node I, and then for local neighborhood for node j, so they can be actually coupled as two like Watson tree. Okay. Say T1 and T2 with Poisson lambda offsprings distribution, right? Okay, so that something let me emphasize. I actually didn't really explain. This notation D here means the D, like the depth, D, like D hop. Okay, sorry, I forgot to say that. So this is a D hop neighborhood. Okay, and then this is the D hop neighborhood of J in B. So as long as D is not that large, D is like growing smaller than like much smaller than log n, then you can couple these local neighborhoods as like a branching process, like Galton-Watson trees, where each step, the number of offsprings is a Poisson lambda. Why Poisson lambda? Is because the number of neighbors is a binomial like n-1 q, right? And then the q is lambda over n. So this binomial will converge to Poisson lambda. So you can make this very formal, yeah. But here I don't want to go into the details. But you can couple them so that the total variation distance is a little 1, for example. Now, if J is corresponds to pi star R, so the I and J are the true pair, it turns out that these two trees, as you can imagine, they should be correlated. Okay? And then if J does not equal to pi star I, so for the fake pairs, you should imagine, or like believe at least, these are independent. Right? Because if you pick any two nodes I and J, they're going to be far away in the graph typically, and then they're going to start like this branching process. They will never like interfere each other too much. So you would have these two independent Galton-Watson tree. So now if you believe this, then this classification problem, like determining whether a particular pair is a true match or not, like should you decide to put it in the set S, just boils down to a hypothesis testing problem again. Under H0, the two trees are independent. Under H1, the two trees are correlated. If you can test them, then you can classify them. Or if you cannot, yeah, and then if you cannot test them, then you cannot really like classify them, right? So that's basically the reduction to a kind of hypothesis testing problem for the correlation in these two Galton-Watson trees. Okay. But it turns out that, yeah, to rigorously define this, I have to do some notation. So I need to give you a formal definition of what is exactly Galton-Watson tree, and then what is exactly the correlation, right? So it turns out that a good way to think about this Galton-Watson tree is look at, first let me define a set of all unlabeled rooted trees of depths at most d. Okay, so this categoric xd just includes all the possible unlabeled rooted trees of depths at most d. And then if I pick a particular unlabeled trees, this turns out that it will be very useful to represent this as the following way. It's a sequence of integers where indexed by like a rooted like a tree with depth at most d minus 1. Okay, so this n tau here is just the number of children whose subtrees is basically equal to tau. Okay. Yeah, so let me give you some example, or let me first draw some visualization. So basically you have a rooted trees. You first look at, it's a depth d, right? You can look at all the children's. Maybe this is like one particular subtree. This is one particular subtree, one particular subtree, one particular subtree, right? And this n tau just counts like because here there's no labeling. So what matters is the topology. So basically it counts like for a particular type of subtree how many there are, right? And then for some other type of subtree how many there are, basically. So let me give you an example again. So for example, I have this particular one, very simple one. This is the depth is 1, right? So if I'm using that notation, what does it mean is that like how many, this is just means it's a singleton. Like it's a very trivial tree. There are 2 of them, right? Because if you look at the children, these 2 subtrees are just like this, right? So there are 2 of them, so that's why you put 2. So that's just a trivial example. If you look at another example, let's make it slightly more interesting. Like this is the depth is 2. Okay, so how does this look like? Well, now you have 2 possible different subtree, right? This is a subtree, this is a subtree, right? So you have this trivial tree, you have 1 of them, and you have like this wedge tree, you have 2. Sorry, you also have 1 of them, right? Make sense? Right? So that's just a way to kind of formally define like all these unlabeled tree. So what does it look like? Okay. Now with this definition, now I can talk about this. Now I can talk about formally what is a Galton-Watson tree. Okay, so basically I'm going to use this notation. It's a depth of D. The offspring distribution is Poisson lambda. Okay, so let this denote this Galton-Watson distribution. So it's actually recursively defined. So if I look at the D is 0, so it's a trivial tree. So I'm going to use in this notation. Sorry, D is 0, and then lambda. So basically then this is a delta mass on this trivial tree. Okay, because there's only one tree of depth 0, it's just a singleton, right? So just put the delta mass. So this is like a delta mass. Okay. But now, if you give me a depth D tree, then using my representation, then I can represent it as n tau, where tau is all the possible D minus 1 like depth subtree. Then when I say this follows this Galton-Watson tree of depth D, what I meant is I look at this n tau, it should be like IID Poisson with rate lambda and times this Galton-Watson tree times the probability I will see this particular type of Galton-Watson tree. Okay? So basically here I'm using this like Poisson splitting property, right? The total number of children I have, like this sum of all these n tau should follows a Poisson lambda. But then I'm going to kind of split them according to different type of subtree. Each type of subtree will give me lambda times the probability for the subtree to be equal to that tau, right? So it's I'm going to using this recursive definition, right? So that's the one way to rigorously define this Galton-Watson tree distribution on the unlabeled trees. Right? Make sense? Okay, now with this, then I can easily define this, formally define this hypothesis testing problem. So for the null model, basically what I'm doing is that I'm just going to take 2 independent Galton-Watson tree, right? So I'm going to use this product distribution. So it just means that they're independent. Okay. Right? So I have two trees. They're just each of them follow independently according to the Galton-Watson tree. And then for the correlated model, is under H1. Okay, here I need to do a little bit more carefully. So let's say I have two trees, T and T prime. I'm going to define this. Okay, so, oh, sorry, let me actually, I think there's still some. So the first thing is that I'm going to define the depth is 0. So this is a trivial one, just the same, P0 lambda. It's like the one that I defined earlier. I mean, there's only, depth is 0, there's only singleton, so it's just a lot. Yeah, there's not much interesting. But now if I look at the depth D in particular, this one, so how this is defined? Well, again, I'm going to write this T and then T prime as a sequence of integers. So T is like this n tau. Tau is x d minus 1, right? And then T prime is, let's say you have n prime, tau prime, where tau prime is also in this set of trees with depth d minus 1, right? So then what I mean by correlated, so I mean you can separate this n tau into two parts, the delta tau plus, let me write down first, then I'm going to explain. Oh, I think I need to do it very carefully. Don't mess up. Yeah. So what I'm doing is a formula. Maybe it's good to draw a picture. So it's just again try to formally define all these different things. I have two trees. One is T prime. So it will have their disjoint part. This is the delta tau part. Sorry, yes. And then there is also delta prime tau prime part. So this part they are disjoint, but they will also have some common part, m tau and tau prime. The m tau prime. Okay. But then when I look at this, I need to marginalize. So I need to sum over all the tau prime. So here I'm thinking about as a pair. So that's why I have m tau prime. And then each of these guys, they're just independent Poisson. They're independent Poisson. So in particular, let's say the delta tau is IID Poisson lambda 1 minus s. So here the s is the subsampling probability. So it's a lambda 1 minus s. And then you have this Galton-Watson tree of depth d minus 1. And then delta prime, tau prime is again IID Poisson lambda 1 minus s tau prime. And then the last thing is this m tau prime. They're like IID Poisson lambda s, and then here this. I should recursively use this. So this PD minus 1 lambda s tau prime. Okay. So basically here in the intuition is that S is subsampling probability. So you have a Poisson lambda offsprings here, Poisson lambda like children here. So that children, they will kind of disjoint. So this is like Poisson lambda 1 minus S. And then for each of them, they're going to have a particular subtree. So that's why you further split them according to the different subtree structure, right? And do the same thing for this disjoint part. For this part, they are common parts. So the children actually matches, right? So then how many of them? There are Poisson lambda S many of them. But then for each children, they will generate like particular tree tau and tau prime. And then according to this like a correlated tree model that like recursive define. Right, so that's roughly how it goes. Okay.
You call the joint distribution of the n-tau and n-prime tau prime PD tau prime.
Sorry, where?
I mean, so I just mean the very last notation.
Oh, you mean here? Yeah.
Yeah, so by recursively you mean what is PD tau prime? It's precisely this pair.
PD tau.
Yeah, I mean,
Yes.
I just mean,
Yeah. Yeah, like here. Sorry. Yes. Yeah. So I'm defining this PD. Yeah, exactly. I'm defining this PD lambda s t comma t prime. So then, yeah, that's exactly what I meant by this.
yeah.
It's a recursive
I
defined.
think it's fine, yeah, but I mean, your last notation, PD minus 1, has this parameters tau and tau prime.
Yeah. It just means that this is all.
It means the two particular entries of
Yeah,
PD.
exactly.
Yeah.
Exactly. Very good. Because this is a distribution on these trees. I mean, they all. Yeah, this is a discrete distribution. So that's why you can directly plug in this particular tree structure. Here, the subtree structure, and then this gives you the probability. It's a number. Yeah.
Okay.
Yeah. Okay. Yeah. I guess, yeah. Unfortunately, I don't have enough time, but I can at least show the result. So the result, just saying that now you have this correlated detection problem where on the H0, T and T prime, they're just jointly distributed according to this independent model. On the H1, this T and T prime are distributed according to this correlated model that I just recursively defined. Okay? Now it turns out that basically the theorem they prove by this set of authors is that they show the following result. So if actually the subsampling probability is less than square root of alpha, so the alpha is the same Ortiz constant, then they prove that if you look at the second moment of this likelihood ratio, and this is illustrated under using this notation, is actually bounded. Okay. So this is actually the part that connects back to the earlier part. If you remember, when we talk about this, showing this detection is impossible, we actually talk about the second moment, try to bound in the second moment of the likelihood ratio. So that's exactly what they're doing here. So they look at this likelihood ratio, take a square, and then take the expectation under this H0. They show this is bounded. And then when it's bounded, this will imply that this distribution will immediately imply this is actually contiguous to this non-distribution. So meaning that if you have an event that holds with high probability here, will also hold with high probability here. Yeah, so that will show that this you will not be able to test them with vanishing error probability and that kind of things. Yeah, so that actually, and then because of the connection to the local algorithm to this testing problem, it further shows that the local algorithm actually won't work when S is less than or equal than square root of alpha. Yeah. Maybe I should stop. Yes.
Okay.
Yeah. Yeah. Thanks.
So that's
Yes.
Any questions?
Yeah.
So there is no conjecture here, like for the low degree polynomials, there was a conjecture, right?
Yeah.
Here there is no conjecture, or are you using some conjecture?
There is no conjecture in terms of this result. So it's a form.
No, but more broadly to show that these local algorithms don't work. So this actually completes the proof. There's no conjecture. Local.
Yeah. I think, I mean, if you believe that connection, I think yes.
I see.
Yeah. I mean, they actually do not establish the connection from local algorithm to this testing problem, but I think this is, yeah. more or less standable. Yeah.
So this is type.
Yeah. They actually have a matching.
Pose.
Um,
Then you cannot.
Yeah. There's a matching result. It's not. Yeah. There's a S is bigger than square root of alpha, but then they also need a lambda to be large. Lambda to be sufficiently large. Then basically you can test. I mean, I'm not going to write down a formal like conclusion, but basically you can. It means that you can test this two hypotheses. Yeah. So it's for this tree detection problem, it's more or less tight. Yeah.
And how did they connect this to the graph matching problem?
Yeah, there's a further step, right? So if you want to using this as an algorithm for graph matching, then you have more steps to do, because
But I mean, is there a formal connection for the lower bound?
Yeah, for the lower bound, I think so. Like, this is the one that I kind of loosely connected to.
I mean, how? What's the? I mean, how did they? Or maybe we can talk about it.
Yeah. So they didn't do that in that paper, connecting.
Okay.
But the general idea is that if you give me a graph matching algorithm that give me partial recovery, then you should be able to classify a pair, whether it's true pair or fake pair, based on the local neighborhood, right? If you look at local algorithm. And then this classification problem, because the local neighborhood converges to the Galton-Watson tree, if you can solve the classification problem, you should be able to solve this hypothesis testing problem. But then below the threshold, this hypothesis problem is impossible to solve. So that completes the entire circle. Yeah.
All right. Any other questions?
Yeah. There's a, I mean, there's a, maybe I can add one line comment is that how to prove the second moment is bounded. It actually using like a polynomial approximation, or it also relates to orthogonal, so they try to expand this likelihood ratio as in a certain polynomial basis. So that actually connects to this low degree polynomial part, but I don't have time to talk about that. But that's how they actually bound this second moment. Expand this likelihood ratio into some certain orthogonal polynomial basis, and then you can quickly compute that. You will see these unlabeled trees popping out immediately, and then you get this condition. Yeah.
All right. So thanks everyone for coming.
Okay.